Today I am going to solve one numerical problem on material derivative and substantial derivatives. Finally, I'll find acceleration of the fluid particle. Here is the problem statement. Consider a fluid particle whose motion is described by the following velocity field, that is capital V, means a vector V is equal to 3y square I plus 5x square zj plus 4t square k. Now we have to find out, means determine both velocity and acceleration vector for a particle located at coordinates 3, 2, 4 when the time is equal to 2 seconds. So first we have to find out velocity and then acceleration. Now here velocity vector is given. Now from that solution for calculating velocity component. Now velocity vector is given here. So that is velocity vector is 3y square I plus 5x square j plus 4t square k. Now we can write as a ui, component wise ui plus vj and then wk. So both I, j, k are unit vector. So u and v and w is a component of the velocity. Now from this velocity vector we can easily write u is nothing but 3y square, v is nothing but 5x square z, and w is nothing but 4t square. That's it. So now here given, so u is, that is component of the velocity, so x component of the velocity, that is 3y square. Okay, so here v is nothing but, we can write 3y square I plus y square, then plus 5x square z, that is j, plus, that is given, and 4t square k. So x I j k is the vector. So here u is the 3y square, v is 5x square z, and w is 4t square. And coordinate is given at point, that is 3 to 4. So x is equal to 3, to y is equal to 2, and z is equal to 4, and time is equal to t is equal to 2. Now what will be the that component velocity? If you plug that x, y, z, means here y square is given only, so y is nothing but 2, so 3 into 2 square, so that is 12 units. V is 5x square z, so v will be 5 into, that is x is equal to 3 is 3 to the plus square, and plus 4, so that is 180 units, and w is 4t square. So here the w is 4 into t is equal to 2 time t, that is 16 unit. So velocity vector v at 3, 2, 4 is v is equal to, v is the velocity vector, 12 by plus 180 g plus 16 k. Now what will be the resultant velocity or magnitude of the velocity? So mod v is equal to root over 12 square plus 180 square plus 16 square. So 144 plus 32,400 plus 256, that is total root over 32800. So 181.1 unit. So velocity vector is 12 by plus 180 j plus 16 k, and resultant velocity or the magnitude of the velocity is 181.1 units. Now coming to the acceleration part. Now acceleration component formula we know, that is ax is nothing but, that is x component acceleration, u partial derivative of u with respect to x, v into partial derivative of u with respect to y, w into partial derivative of u with respect to z, and plus partial derivative of u with respect to t. Similarly, that this is x component, then this is y component acceleration, and this is z component acceleration. Now we know u, v and w, right? So now we have to do the partial derivative for each term and then plug, and then we'll get the acceleration in individual direction. Like first we are going to calculating the acceleration component by partial derivative. So what will be the partial derivative of u with respect to x? So u we know, that is 3y square. So partial derivative of 3y square by that with respect to x, so that will be 0, because here no x term is there, so 0. So that del u by del y, so that is nothing but 6y del u by del z, so del 3y square by del z, so 0, del u by del t, so that is 0. Similarly here that partial derivative of v with respect to x, so if I do the calculation, so that will be del by del x 5x square z, so that is del x z, del v by del y, so that is here no y term is there, so that is 0, del v by del z, so here no z is there, so 5x square. Okay, so partial derivative, if we know that partial derivative, we can easily calculate. And del v by dt, so here no t term, so that is 0. Now here for w is actually function of only t, so dw by del w by del x, so that is 0, del w by del y is 0, del w by del z is actually 0, so del w by del t is nothing but 80. Now we got all this component wise component acceleration component by partial derivative. Now we have to plug this all values. Now here, so we got this, okay, this we got. Now evaluating this at x is equal to 3, y is equal to 2, and z is equal to 4, and t is equal to 2. So du by dy, so that will be 12, dv by dx, that is 5x square, dy by dx, sorry, 10xz, 10 into 3 into 4, 120, dv by dz 5x square, so 5 into 3 to the power square, 45, and dw by dt, so 8 into 2, 16. Other terms are zeros. Okay, so now we got this component. Now go back to that component term ax, so ax is equal to this, so we plug all these values. So u is 12, but that del u by del x is 0, v is 180, del u by del y is 12, w is 16, but del u by del z is 0. So u, v, w we already calculated in that first slide. Okay, and del u by del t is 0. So finally we'll get ax is actually 2160 units. Similarly ay and az, ay will be 2160 unit. So we plug all this u, del v by del x, v del v by del y, w del v by del z, plus del v by del t. So we'll get that acceleration at that y component 2160, acceleration in the z component, that is 16. We plug all this value, we'll get 16. So component wise, that x direction acceleration is 2160 unit, y direction acceleration is 2160 unit, same. Okay, and then az is 16 unit. Now finally acceleration vector a is nothing but axi plus ayj plus azk. So we plug all this value. Okay, so we'll get the acceleration vector 2160i plus 2160j plus 16k. Now finally that what will be the magnitude of a, so resultant acceleration or magnitude of that acceleration, so that is root over of ax square plus ay square plus az square. So that square root of 2160 square plus 2160 square plus 16 square, ultimately acceleration is 3056.6 units. So we got that velocity vector, velocity, magnitude of the velocity, acceleration, and magnitude of acceleration. So that's it. Thank you.